question says, integrate the function z over the region above the cone x squared plus y squared equal to z squared, and below the sphere rho equals to r. So we don't have an actual numerical value for the radius, it's just in general r. What I'm going to do, you're going to calculate the following triple integral. Triple integral f of x by z dv, or you can convert that into spherical coordinate. dv becomes rho squared sine phi d rho d phi d theta, but we need to find the boundaries for each. So let us find the bounds for each variable. What I'm going to do, I'm going to start by working on the cone. Work on the cone. You have x squared plus y squared equals to z squared. So basically you have rho squared cosine squared theta sine phi to the second plus rho squared sine squared theta sine squared phi equals to rho squared cosine squared phi. Very good. So here I can factor out rho squared sine squared. On the left, I have rho squared sine squared phi, and I end up with cosine squared cosine squared plus sine squared theta, which is basically 1. And on the other side, I have rho squared cosine squared phi. So this is just trig identity, which is 1. So we end up having canceling rho squared and rho squared. We have sine squared phi equals to cosine squared phi. But if you take square root of both sides, you end up with sine squared phi equals to plus minus cosine phi. So we're looking for angles phi that makes sine and cosine equal or opposite of each other. Those angles from pre-calculus unit circle are going to be pi over 4 and 3 pi over 4. That's enough for us. Why? Because we look at phi in general. Our phi by definition is bounded between 0 and pi. So these two should be enough for us. Perfect. So what's next? We know that our phi is bounded between 0 and pi over 4. Why is that? Let's take a look at the graph a little bit. If you check the graph, here you have a cone and you have sphere, rho equals to r. So sphere is a little bit easier to work with first. This is my sphere. And then this guy is rho equals to r, or just let's write down r in general. And for your cone, x squared plus y squared is equal to z squared. For this, you have the following cone. Cone x squared plus y squared equals to z squared. And since x, y, and z are positive, we expect phi to start from 0 and stop at pi over 4. So this equation, x squared plus y squared plus z squared, which is your cone, can be also identified by phi equals to pi over 4. These two are equivalent to each other. So an exam, and homework, if you see instead of x squared plus y squared equals to z squared, you only see phi equals to pi over 4, it refers to this cone here. Very good. So we just identify phi bounded between 0 and pi over 4. What about theta? Theta has a complete rotation. Theta is bounded between 0 and 2 pi. What about your rho? Rho is bounded between 0 and the maximum value we can take is r, because of the definition of rho here. You just need to set up the integral and start computing this triple integral. So let me find the eraser. Oh, sure. So this triple integral is the integral 0 to 2 pi for my theta, integral 0 to pi over 4 for my phi, and my rho is bounded between 0 and r. And here I have f of rho phi theta, which is basically z, but z is rho cosine phi multiplied by rho squared sine phi and d rho d pi d theta. Can combine these two, you get r to the third. Well, you can separate these as well. You have fixed boundaries. And there is no combination between rho, phi, and theta. So you can separate these into three integrals. 0 to 2 pi of d theta multiplied by 0 to pi over 4 cosine phi sine phi d phi, and integral 0 to r cubed, rho cubed d rho. So this is just 2 pi. Here you can use u sub. If u is equal to, for example, sine, du is cosine, so you have a half u squared or sine squared phi bounded between 0 and pi over 4 multiplied by 1/4 of r to the 4. So you can cancel out 2 and 2, so you have pi, and the sine of pi over 4 is 1 over square root of 2. It has exponent 2 multiplied by 1/4 r to the 4. This guy becomes pi over 8 r to the 4. So as long as you have a value for r, you can plug that in and find the actual triple integral.